So I wanted to just take a minute and talk a little bit about what the heck it is we're trying to learn in this class. Sort of take a little bit of a zoomed out perspective here for a few minutes. And think about what it is exactly that we're trying to learn in this class. Because this class is a little bit different than some of your other classes. I really think this class is a skill class. I think that learning physics really is a skill. To me, it's much more like learning how to shoot a basketball than it is learning who was president in 1982. Right? If I asked you a question, who was the president in 1982? Well, you just either know the answer or you don't. And if you don't know the answer, you go look it up. And then you sit there and you stare at it and say, Ronald Reagan, 1982, Ronald Reagan, 1982. And then when I give you the test, it says who was the president in 1982, and you go Ronald Reagan, 1982, and you write it down. Bam! And you get your points. That's not what we're doing here, right? This is much more like learning to shoot a basketball than it is memorizing a list of facts. So I wanted to take just a minute and talk about what it is we're trying to learn in this class and how you might be able to apply that to more effective studying strategies. So, what is physics? Well, physics is a study of motion, electricity and magnetism, gravity, light. It's the study of atomic structure. All of these things, that's all true. That's all true. But that's not usually mostly what I test you on, is it? Or what the homework questions are about, right? Like, let's take a specific example from Physics 1. Let's take Newton's second law, for example. So, Newton's second law. Better known by its equation form, which is the sum of the forces equals mass times acceleration. Okay. So that's a physical principle that we learned about in Physics 1. Okay, so if you're approaching this from sort of a memorization, a list of information to assimilate perspective, then that's kind of the end of the story, right? What does Newton's second law tell us? It tells us a relationship between force and acceleration, right? It's a cause and effect relationship. Force is the cause, the effect is acceleration. How much acceleration do we get? Well, it depends on how much mass we have. Okay, so if I'm just asking you straight up memorized questions, that's kind of the end of it. I can ask you what Newton's second law is. You could tell me that Isaac Newton first published it in the Principia de Mathematica in 1687. But honestly, that's not what I'm going to ask you about this, right? I'm going to ask you about its application. So let's think, let's back up again and talk more about what is physics. Okay, so in the 1600s, Isaac Newton comes up with this idea. F equals ma. This is not something that can be logically proven, right? You can't logically show that this is true. You just can't, right? So Isaac Newton says, I think this is what the world, I think this is how the world works, people. I really do. I think the world works like this. And along with this come some definitions, right? In order to believe this mathematical equation, we need to know what each of these symbols represents, right? So Newton says, I think the world works like this. As long as F means a push or a pull in a certain direction, mass is the object's inertia, or how much stuff, and acceleration is a change in motion, a speeding up, a slowing down, or a turning. If we accept those definitions of these three symbols, then Newton says, I think this is how the world works. Now, he published this in the 1600s, and we're here in the 2000s, it's 2020 right now, and nobody's found a problem with this, right? We're pretty sure this is how the world works, but it's important to recognize that this is not a result that Newton reached logically. It's a result that Newton reached by experimentation, right? He says, I think this is how the world works. And we're pretty convinced of it at this point, and we call it Newton's law because we're pretty darn sure it's right. Now, what can you do with Newton's law? What is the point of it, right? So, what is the point of it? Well, you can use Newton's law to build something. For example, you can build a skyscraper, and you don't just have to build it and just see if it falls down, and if it does, we'll change something and build a new one. You don't want to do that with your skyscraper, right? You want to have a better strategy. You want to be able to go in ahead of time and say, hey, I did all this math, and I don't think my building's going to fall down. Well, what was your math based on? Was your math based on Ansell's fourth law? Because nobody believes that, right? No. If your math was based on Newton's second law, and your math is correct, and your math says the skyscraper will stand up and it won't fall down, then we have reason to believe that your skyscraper won't fall down. So what can we do with Newton's second law? Well, we could build a skyscraper. What else? Build. What else could we do? We could analyze, we could design an airplane. Any type of design of any structure or any object is going to require Newton's second law. I can, I know what I can do with Newton's second law. I can land a person on the moon. Okay, so now you might say, oh, this is just a little equation. How can we land a person on the moon with Newton's second law? That's the point of physics, is that we take this general principle. In 1600s, Isaac Newton says, I think this is how the world works, and we apply it to specific situations. As long as our logic is sound, then we believe that the person will go where our math says it will go, right? If we're starting with a principle that we believe, right? Again, we start with a principle we all agree on, we apply logic to it, and we trust our result as long as we started in a place that we agree with and our logic is sound. Okay, so that's where logic goes. What is the form of that logic? It's mathematical reasoning. And so this is where we're getting into what do we do in this class, right? So if we just look up what is physics, it's the study of motion, gravity, electricity, magnetism, light, all these things. But fundamentally, physics is a mathematical science. So we don't just sit around and talk about the colors, right? We apply mathematical equations to light, right? So in physics, we create models. The model is not the universe. The model is a representation of the universe that is useful. In physics, those models are mathematical in nature. This is a model of how the universe works, and it is mathematical in nature. How do we apply this model to a specific situation? Logic, yes, but specifically mathematical reasoning. So, math, reasoning, right? That's what leads us from a general principle to a specific example, right? From a general principle to a specific conclusion. What gets us between those two? Logic. What is the form of that logic? It is mathematical reasoning. So, okay, so these are sort of real world things that we might apply Newton's second law to, if we were late in our careers and had some fancy job. I don't know. We're not going to build a skyscraper in physics too. What are we going to do in physics too? What might be the type of problems we might answer? Find the tension in the rope, right? Rope. Pulling a cart. I don't know. Right? This is the type of problem that we might use Newton's second law for, right? If in a physics class, in an introductory physics class. Okay, well, what else? We could, find, find the, how fast is something going? How fast is a sled going? After, some time, 3 seconds, I don't know. I'd have to give you some more info, right? So how fast is a sled going after a few seconds? Okay, so that might be the kind of problem I would ask you, right? How fast is a sled going after just a few seconds? Now, how are we going to do that? So the point of the class then, the point of what we're learning is connecting the general principle to the specific situation, right? And now how do we do that? How do we do that? Well, it depends on what class you're in, right? So if you're in the conceptual physics class, and there's different names for it depending on what school you're at, this is going to be fairly straightforward, right? We might do the kind of question of like, so if you're in the conceptual physics class, it might be, a truck has a certain acceleration. What's the acceleration of the same truck if it's hauling a trailer that has the same mass as the truck itself? Oh, we can use proportional thinking. We have twice the mass, the same force, we get half the acceleration. Okay, that's the kind of problem you might be asked if we are in a conceptual physics class. Now, if we are in a class like we have, an intro physics class that's basically algebra based, then we're looking at mathematical reasoning leading from the general principle to the result. And generally, what does that look like? Mathematical reasoning in the form of algebra and trig, right? So that's how you're going to get from the general principle to the specific situation. That is the crux of what we are teaching you in this class. That's what we're learning here, right? So we're trying to use algebra and trigonometry to go from the general principle to a specific situation. If you were to take calculus-based physics, then we'd include calculus here, right? So depending on how advanced the course is, how challenging is the mathematical reasoning connecting the general principle to the specific situation? That's how we make a harder or an easier intro physics class. But this is what we're learning. Connecting the general principle to the specific situation using algebra is what we are learning. So I want to talk just a minute now about what the goal of quiz number 1 was. I'm going to erase the board. I'll be right back. Okay, so in the quiz we had our 2 charged balloons. They were repelling each other. And I asked the question, what is the charge on one of these balloons? So, to go back to our sort of structure, what are the big principles we're going to be using here? Well, we needed to use Newton's second law, and Coulomb's law. Right? These are the general principles. We're trying to apply it to this specific situation in order to find the charge. How are we going to do that? Math. Okay, so big picture, what's the point of the quiz? What's the point of what we're learning in this class? Well, is it to know Newton's second law? Sure, but you can kind of look that up, right? I mean, sum of the forces equals ma. The point is not that you know Newton's second law. It's just not. You already know it. You looked it up. I don't know. Is it to know Coulomb's law? It's not really to know Coulomb's law. Hopefully it's helping us wrap our brains around what Coulomb's law means, but those are the 2 things, the 2 big ideas we're talking about. What is the quiz supposed to help us practice and learn? The mathematical reasoning to apply it to the specific situation. I also don't really care about the charge, right? A different balloon will have a different charge. I don't know. I mean, the exact number is not super interesting. I mean, it's kind of interesting to know that we've got something like 10 to the negative 7th coulombs when I rub it with a piece of cloth. That picture that I included in the quiz was not a real picture that I took of a situation that I created, but when I get to teach this class in person, I just set this up in the front of the class. I find a rabbit fur and I rub the balloons, and you just see this nice situation that happens. It works out great. So that's sort of interesting. It's sort of interesting to know that there's about 10 to the negative 7th coulombs on those balloons, but that's not the point, right? The point is this right here. That's what we're learning. That's what I'm going to test you on. That's what you should be practicing. Okay, so what this means then is that if you went to the internet or some other resource and you found this setup and you found this equation and you wrote this down and then you solved for Q, did you find Q? Yeah, but you completely missed the point, right? The point is absolutely not to go hunt around and find this equation. This is correct. Some of you found a version that had a 2 in it, so I saw a lot of that. I think it was probably supposed to be under the theta, but maybe you wrote it down wrong. I'm not sure. Some people had that. I really don't know where that came from. But a lot of people had this, which is correct. But it's not one of our general principles. This is not a general principle. This is not in a physics textbook. There is not a section in our textbook called 2 balloons hanging from strings with identical charges. Right? No, it's not a general principle. This is not a general principle. This is a general principle. If you don't know how to get from here to here, then you didn't actually do the quiz, right? You just didn't, because that's the point is, can we get from here to here, right? And so if you just found this equation and wrote it down, it's just not the point. You might as well not even do the quiz, frankly, because it's just not what we're learning, right? And I understand, and that sounded harsh a little bit, and I don't mean like I'm not being grumpy about it. I'm simply trying to explain what we're trying to learn here, because I really think it is different than the way we approach other classes, right? I think a lot of you have gotten really good at approaching your other classes, and it's where you have a list of information, you memorize it, you regurgitate it. You memorize it, you regurgitate it. And maybe in a history class or something, your teacher really wants you to analyze that info. And that's great. You know what usually you can do? You can usually just, your teacher will usually analyze it in class. And if you just memorize that and regurgitate that on the test, you're going to get your A, right? It's just not like this. It's just not like that, right? I can ask you questions on the test that you've never seen before. Why? Because what we're learning is the mathematical reasoning. We're not learning about 2 balloons on strings. We're learning about mathematical reasoning. It's a mathematical problem-solving class. It is not a memorize some stuff class. So let's look at what the solution that I was looking for looks like. Okay, first we're going to draw a free body diagram for the balloon on the right. We have tension over here, electric force over here, weight here. There's Tx, there's Ty. Of course, we know that Tx is equal to T sine of theta, Ty, T cosine of theta. Okay, so there's our free body diagram, all of the forces. We're applying Newton's second law, the general principle, to our specific situation. We've drawn our free body diagram. Now we do sum of the forces equals mass times acceleration. In this case, it's not accelerating. And so we have the sum of the forces in the x direction equals 0. We see here we have a positive Fe. I should have told you what I meant by positive. There's x, there's y, standard coordinate system. We have a positive Fe and a minus T sine theta equals 0. Plugging in Coulomb's law. Great. Notice we have 2 unknowns. We don't know T and we don't know Q. So we're not done. We need to do another equation. We'll do the sum of the forces in the y direction. Also equals 0, not accelerating. So in the y direction, we have positive Ty, T cosine theta, and we have minus mg, the weight, equals 0. 2 equations and 2 unknowns. Now I can do some algebra. Let's see, I will go ahead and solve this for t. T equals mg divided by cosine of theta. Now I can plug that in up here. K q squared over r squared equals mg over cosine of theta times the sine of theta. Okay? Notice that sine over cosine is tangent. And so now I'm going to come back over to here. No, I guess I'll just write below here. Okay. I'm going to come back over to here. My board is kind of small. So it goes. Okay, here we go. K q squared over r squared equals mg sine over cosine is tangent. And there is that equation that I was referencing a few minutes ago. Again, just looking this up misses the point, because what we are learning in this class is this problem, right? Is this process, excuse me. This algebra right here, that is the point of the class. This is not the point of the class. This is the point of the class, right? And this is mostly a review of Physics 1, but there's some things that are so universal you can't get away from them, like forces, right? Forces, you can study physics for many years and still be dealing with forces. In fact, this is a free body diagram. Free body diagrams are not baby physics. If you were to go into the basement of the library and where they keep all the journals, and you were to look at the most recent version of Physical Review A, which is where, if you are the most awesome physicist in town, that's where you publish your work, right? And if you look in Physical Review letters A, or Physical Review A, excuse me, then you know what you're going to find? Free body diagrams, okay? So this is real physics. This is what we're learning, right? Now, at this point, we can do some algebra, and I felt like most people felt okay about this, right? We end up with Q equals the square root of mg r squared tan theta over k. And at that point, we plug in our numbers and we get an answer. There were some details there. A lot of people plugged in 15 centimeters instead of 30 centimeters for r. Remember, r is not the radius of the round thing in the problem. R is the distance between the centers of the charges. So again, what did we do? We took a general principle, Newton's second law and Coulomb's law. We applied it to a specific situation to get a result. That's what we're learning to do. That's what we should be practicing, right? And so you need to be practicing, starting with the equations that we get in class, in the lecture. And I recommend you keep yourself a list of those, because it'll be very handy when you're doing the homework, very handy when you're doing the exam. Keep a list of those equations, learn how to apply them to a specific situation. Okay, so I'm going to be having to ask you test questions. I'm going to have to ask you multiple choice test questions that you're going to be taking at home with no proctor, right? So to me, telling you can't look up answers is not particularly useful, right? So it's going to be open everything, which means you'll be able to look answers up online, which means that I can't ask you just the standard questions that you can look up on Chegg. And if people don't know what Chegg is, it is a for-profit company traded on the New York Stock Exchange that will allow you to copy your homework for $14.99 a month. And so it exists. If you were not aware that it's out there, you can do that, right? I don't recommend it at all, because if you copy your homework, you won't be able to do the exam. And so again, back to what am I going to do when I go to write the exam? Well, I'm going to have to try and find a way to ask you questions from the intermediary steps, right? What could I say? I could say, here's a multiple choice question. Which equation gives the sum of the forces on the right balloon in the x direction? I could ask that and give you a series of questions. Of course, the correct answer would be right here or right there, either of those forms, right? I might include this, I might include that, I don't know, right? So that's a question, that's an example of how I might be able to ask a test question that was multiple choice, where I'm asking you to get into the weeds of the solution and not just asking the end, right? Because if you go to Chegg or something, you're just going to see this answer, right? So that's the way that I might formulate a test question. And so part of why I'm going through all this is just to help let you know that this is not what I care about, right? That's not what I care about, right? That's not what we're learning in the class. It's the process. And so that's what you need to be learning in the class. That's what I'm trying to teach. All right. And again, it's practice, 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 practice. That's the only way we get good at anything. It's real easy to get in a negative cycle of thinking in your head and not even realize you're there, and not even realize that you're there. It's easy to think that you can't do this math, but I'm here to tell you that you can. You can learn this. You absolutely can. I mean, if you saw some guy walking down the street, big old muscles everywhere, you would never think to yourself, wow, that guy's really talented at having big muscles. No, you would think to yourself, boy, that guy really likes to hang out and lift heavy stuff, right? I mean, because that's ultimately what it is. And it's the same thing with math, right? When you see maybe some of your peers that have an easier time with this than you do or something like that, you might say, wow, they're really good at physics. They're really talented at physics. Well, that might be true, but it didn't accidentally happen, right? If you are good at anything, and I suspect that each of you is good at something, it is because you practiced. It is because you practiced a whole lot, right? I'm pretty good at playing the guitar, and people will say to me, wow, you're so talented. I wish I could do that. And I say, well, you know what? I probably do have a knack for it, right? But I've also spent countless hours in my basement hanging out by myself practicing, right? It's not just random, right? It's not random. And this stuff is the same, right? Again, physics is more like learning to shoot a basketball than it is like learning who was president in 1982. And I suspect that if you sit down and do a physics problem and you get stuck, some of you may fall into the trap of thinking, oh my gosh, I am no good at physics. And I want to encourage you to not do that. I want to encourage you to think, oh my gosh, I need to practice more. Oh my gosh, I need to ask more questions. That's what I want to encourage you to do. And I think also a lot of times people have this idea that there's never been some mean person in my life who told me that I sucked at math, right? I think that sometimes when people think about, we hear about the gender gap between male and female achievement in mathematics, which starts to show up right around puberty, unfortunately. So we hear these things and we might think, I can't believe all these women have these people in their lives that are telling them they suck at math. I don't think that's the main driver here. There's probably a few situations where somebody was not nice. But I think it's deeper than that, right? You might believe you can't do this math even though nobody's ever told you that, right? You might... I know I have had these hang-ups, right? Like, I'm a good guitar player. You know what? I am not a great singer, right? And it's only been the last few years that I've improved at my singing, because for years and years, I just thought that I kind of sucked and that that's just the way I was. And I'm still not a great singer. But you know what? I've changed my mindset. And what it is I had a lesson with a really great teacher. And he was just like, oh yeah, you need to practice more. And it sounds so simple, but it was mind-blowing to me. It was like, oh, and it gave me the confidence to actually practice. And guess what happened once I started practicing? I started improving, right? And now I'm out of that. I'm out of that mindset where I'm like, I'm just a crappy singer. No, I'm not the singer I want to be, but I'm practicing. And it is not because some mean person in my past told me I was a bad singer. In fact, I got quite a bit of positive reinforcement growing up on my singing, but there was a million little tiny things when I was not very successful at singing that all added up. And one thing that an ex-girlfriend said one time when I was 16, and she wasn't trying to be mean, it was just something that she said, and it stuck with me for years. Anyway, if you think you can't learn the math, you can. I promise. I promise, promise, promise.